Thank you all for coming. We're very grateful to have meteorologist Roger Hill here tonight, and his talk is titled Climate Change, the Latest and Some Things Unforeseen. And he will give us some updates about climate change and talk about what is ahead for Vermont, the growing variability of spring, summer heat, and winter cold, and what the lack of sea ice has in store for us and our planet. And he'll talk for about an hour and a quarter, and then he will take a few questions. So, thank you for coming.
Thanks for coming out on a very snowy night, and not very snowy, but I think it's what we're all kind of hoping for eventually, right? So yeah, we might maybe end up with 10 inches on the other side of the weekend. Little three storms coming in, so that would be nice. I know there's a lot of very depressed skiers and cross-country skiers and snowshoers like myself, and just people who like to have snow, and there's a lot of psychological reflectivity, you know, of the snowpack, and it just makes things a whole lot better, I think, especially when when the sun comes out. There's nothing like it. And of course, we cherish snow, so bring it on. Well, my talk is going to be about some of the things that are new, a little bit of review. I also did a presentation for the Sustainable Montpelier, and I'm going to add to some of that and go over some of that stuff too, because there's a lot of interesting things going on in climate right now because of the way it affects weather, and mostly has to do with winter. And we're going to get into a little bit of that. I have a lot of slides, so I just want to warn you. Some of that stuff I'm going to go through pretty quick. Some of it is a little tedious, and I want to spend too much time on a few things, but other things will slow down and get the important stuff out of the way. So thanks very much for coming in, and we'll proceed. This is my disclaimer and attributes. You can see the papers there, the peer-reviewed papers. These are, of course, the researchers and the climate scientists, climatologists, various experts in different fields. And they do quite a bit of the work that, of course, we presenters talk about. And they're very, very important. Of course, being a climate scientist nowadays is not a real good situation psychologically. It's a little bit of a downer, I guess, but we need to know more and more and find out some of the feedbacks and what's going on, and that's what we'll be talking about a little bit. I'm going to skip that slide because I forgot to update it. So the new normal. So, you know, you see the jet stream here, and that's part of what we're looking at, some of the changes that are taking place with the jet stream beginning to slow down a little bit, and what that is caused by. But we're going to kind of do a little bit of a summary here as I go along. So this next slide here, I want to show you, okay, that is the, of course, the problem, but this is what that smokestack was producing, if you will. And you might notice that I have the mediums, the mainstream press talks about carbon dioxide levels too. Well, that's mostly what we tend to talking about. But if you put all the greenhouse gases together, you come up with higher amounts, unfortunately, that have that interaction with sunlight that excite the little molecules and move them around and generate heat. And so that's the name of the game there. So as you can see, the carbon dioxide levels, we're kind of back to that because it's one solid measurement chemically. The levels are the highest, of course, in 3 million years, and that's a long time before humans were around, for example. And the temperature is responding, although not evenly, across the globe. January 2020 is the 420th consecutive month in a row that has been above normal for the planet, warmer than average. So let's look back a few 100,000 years. This is the Vostok ice core and in Antarctica. And so basically what we're seeing is a corresponding of carbon dioxide with temperature. And carbon dioxide, of course, is very much linked. It's basically a thermostat to our atmosphere's temperature. CO2, the highest in the last 3 million years. Of course, that's where we are right now, and you can kind of see just how out of whack things are, unfortunately. And the temperature has yet to really respond. This is the latest Mauna Loa carbon dioxide on the top of Mauna Loa, the southern volcano on the Big Island of Hawaii, a pristine environment. And what you can see here, just to cover, is where we are right at 2020 and how the averages are still going up. And unfortunately, they're not really stopping. They might even be getting a little more accelerated. Just how out of whack carbon dioxide is compared to what it has been. How do they know about all this? Well, they can take the bubbles in the ice core samples, take those little bubbles and do incredible measurements on that to find out exactly what the atmospheric chemistry was thousands of years ago. And hence they can reconstruct the temperatures. Sometimes they use proxies, but sometimes it's just straight right out of the little bubbles out of the ice cores. Well, I had to lead that with this, unfortunately. So this is the course that we're on, and you can see that we have a few choices here. Of course, the best case scenario is the green line there. The middle ground is maybe the way we were kind of trending up through maybe a decade ago or whatever. And we're basically on that red line, unfortunately, and we're going for the highest amount to put the most CO2 and greenhouse gases in the atmosphere, as if it's some sort of race, as if it's some sort of apocalypse. And this is the response. This is the temperature. So what we have two lines here. You're looking at the land temperatures of all the continents as measured. And then you're looking at the ocean temperatures, and you notice the ocean temperature warms a little bit slower because it's like boiling a pot of water. It takes a little while to boil that pot of water, so there's a lot more energy has to go into that to boil that, to get that going, compared to the air temperature. So the air temperature of the land is really rising. You can see the pretty steep curve. It's not 100% linear, it's not a straight line, but the averages come out to that. And there's a lot of course, noise in the system, and that's what we call, variation, sort of natural variation that we see with El Nino and La Nina and other cycles throughout the climate cycles throughout the Indian Ocean, the Pacific, the Atlantic, and so forth. So look back at 2019. This is the latest information, pretty much hot off the press. And 2019 was the second wettest year on record. In the United States, the temperatures were above average despite the regions that were among the only cool spots on the planet. And it's been true, and we're going to get into some of the relationships as to why. The interesting thing is that North America, and typically the parts of the United States generally east of the Rockies, have, for whatever reason, been the coldest temperatures over the last few years. Pretty much everywhere else in the world, it's been right off to the races and very warm. So this is 2019 temperature, looking at the United States. So you can see, interestingly, Vermont kind of averaged a little cool. Of course, we had a very long winter. It was a very cold winter. And it kind of knocked the averages down. Otherwise, we would have been warmer than normal, like most of the country. What we have been noticing is a signal most recently is the Southeastern United States. You can see that at least in 2019, it's been pretty warm there. Out west and in the upper Midwest, the plains, the Rockies, that's where some of that colder air has been kind of displaced out of the Arctic. And that's kind of the connection. How wet was 2019? You can kind of see where the real hot spots were. And there was some in Vermont. You can see in parts of the Northeast US. But for the most part, it was the upper Midwest, lower Great Lakes, Ohio Valley, mid-Mississippi Valley, and so forth. Remember about all the fields that were flooded back when we had that sort of stuck weather system in the spring, where we were really concerned about food and whether or not farmers could get their crops in and then grow anything. I think since then it's gotten better, but pretty scary scenario, and there was a lot of damage done early on. So this is showing how wet we are in Burlington on a local scale. For example, 2019, this is just pretty much hot off the press as well. And what we have is I'm sure a lot of folks remember 2011, especially around here. 2011, of course, was the year that Hurricane Irene hit us. But even prior to that, we had training thunderstorms that were pretty amazing. I remember it well. It was May 27th, and it flooded like crazy in many, many locations in central Vermont. And even in Burlington, though, that reflection showed up there in 2011 being the wettest. The driest, you can see there is 1894. And we've been kind of in between on the average, but we're running still above average. And so 2019 was a little bit wet. And all you have to do is remember back to, I believe it was June, was a pretty ugly month, and we had a ton of rain. And also in the fall prior to that. More US downpours. This is not 1 inch, it's not 2 inches, it's 3 inches. 3 inches in one day is usually going to get the job done for flash flooding. It depends on the antecedent conditions, the ground, how much soil moisture there is, how much saturation and whatnot. So let's say we just had a heavy wet soaker come through, we had another heavy wet soaker come through. Now you've got your ground is very saturated. So the next system that comes through is going to be obviously even more of a problem. And it means it takes much less to get runoff. And runoff is the name of the game, especially in the Northeast United States. More downpours. You can see that we're kind of the hot spot, 55%. 9% out in the Pacific Northwest. They're starting to see a little bit of an uptick out there, and kind of in between so far in the desert Southwest and the Southern Plains and whatnot. This is something that's interesting. Climate Central had this, and it's the power of trees. And trees are a very, very good thing for climate change. Why? Because there's so much water vapor, there's so much rainfall coming down heavier, more intense, and the roots of trees is very, very important. For example, you take the 1927 flood, we had a lot of rain with that, and the antecedent conditions ahead of that was very, very moist and very wet, so we had high soil moisture, the runoff situation, whatnot. But we had a lot of trees that were cut. Of course, in Vermont was a lot less forested. Well, that's a huge contribution to runoff. And runoff is a problem, of course, for us because much of our towns are all based along rivers. They're mill towns and whatnot, using the river as a source of energy. So a lot of our towns, a lot of our roads to get to our towns are right along the rivers. So this is an issue, and it's going to be probably getting more and more notice because we're going to unfortunately see more and more flooding. Runoff avoided by trees, kind of interesting there. You take a look at the Northeast United States, you can kind of see that. Also the Pacific Northwest up the California coast, coastal regions, sort of in the upper Midwest, lower Great Lakes, and down in the, looks like the mid-Mississippi or southern Mississippi Valley, lower Mississippi Valley, and a lot of trees. Where there's no trees, good luck. So back to warming now, and this is new data. We just turned to 2020, now we have new climatology. We got a full decade to go back on. Of course, not all the information's in right now, but you can see for yourself that the 2010s have been the warmest, and temperatures are going up. We have to go back to the 2018 record. I don't have 2019. It's just not quite in. I think it comes out around the 15th of the month, tomorrow. So we're missing it just by 1 day, but you kind of get the picture there. What it looked like last year was the 4th hottest year on record, significant in itself. Of course, even going back last year, they had incredibly warm Europe. You can see that they were pretty much very, very warm. The other thing you might notice is just south of Greenland there is kind of a blue spot. That's a cold spot. And that cold spot is related to meltwaters coming off of Greenland, that then that fresh meltwater sits over there and it doesn't sink, and that kind of slows down the conveyor belt system, otherwise related to the Gulf Stream. And that is another kind of a feedback that's taking place with the Gulf Stream, with the feedback of the oceans in the atmosphere. The hottest years on record globally, the last 5. You can see where 2018 ended up with. This is, we're going to spend a little more time on this because it's how we know that carbon dioxide is affecting the atmosphere. So if you look at the top chart there, you can see solar plus volcanic, natural. Let's say humans didn't exist. There was no cars, there was no coal being pulled out of the ground and then burned for whatever reason. You can see that observed temperature goes up and down. You see the natural variation. Okay, so you can see the modeled temperature, and what the modeled temperature would do based on the conditions of volcanic ash, El Nino, several other sort of natural variations. And you can see how they separate there about 1960. Well, that blue line is where we should be if we didn't have greenhouse gases in the atmosphere that we put in. Instead, we have that line up there on that top graph going up, and that is related to our changing climate. It's warming. Now, if you look at the bottom here, you can see how that matches very nicely. So when you apply greenhouse gases through the technology, through all of the various ways of interpreting computer modeling, you come out with these lines basically showing the observations, and then you can see obviously it matches up pretty good. And the models, the climate models are really catching up, and they're actually very, very good. So what the heck is going on? Is human-caused climate change real? Okay, so global temperatures. What we have here is, we've already, first of all, the Paris Climate Accord was to try to keep everything under 1.5 degrees Celsius. And we've already hit 1.5 degrees Celsius in some spots. And that's namely, looks like this is in 2016. It was an extraordinary year, and probably what happened, if I remember correctly, 2015 was a pretty strong El Nino. When you have an El Nino, which is surface warming in the subtropical Pacific, you put natural variation of El Nino on top of climate-induced warming through greenhouse gases, you come up with this. But most of the energy is going into the oceans. And so we're seeing actually very little of the energy that's creating the warming right now is actually happening in the atmosphere. It's mostly going into the oceans, which then interact with the atmosphere. Whoops. So this is, think summer, kind of an opposite situation to right now. Let's say we had a great snowy winter and it was fabulous and we had tons of snow and then it all melted and out in, I don't know, pick a date, a week after town meeting, maybe the perfect situation. And then we got through mud season really quick and now we start to have flowers coming up, green grass. We're headed into summer. Well, those summers are getting hotter. Vermont it's as if Vermont has migrated to around Binghamton, New York. You see that? And then we have the highest emission scenario and the lowest emission scenario. And you can see how, if we continue on the course as business as usual, which we are, we're headed for, I don't know, northeast, either northwest Georgia or northeast, what is that, Mississippi? Alabama. They have great music in Alabama, and the barbecue is supposed to be excellent. I've never been there myself. I got to go. All right, so fastest warming seasons is not in the summer, though. It's the winter. What happened over the weekend? We broke records, right? 60 degrees, 60 to 65 generally. crazy stuff. So climate change is really affecting our winters much more than our springs, our falls, or our summer. And that's kind of the name of the game. That's the trend. So getting back on a local scale, just to sort of measure that out back to winter, what we're looking at here is the Lake Champlain freeze updates through 1816 through 2014. And note the diamonds. These are the little diamonds here. The diamonds, no reported freeze. So you can see the diamonds increased after 1944. We had more and more diamonds right up through 2008 and so forth. Obviously, it's a proxy showing the warming and how erratic or variable, at least some parts of our winter, is going to be to that formation or non-formation of ice. Other changes we use for proxies can be the freeze dates. You can see that our growing season is getting longer because we're having warming temperatures, so we're getting an earlier spring and a later fall. Not always, and there are some curveballs I'm going to show you. Precipitation, the number of days per year with greater than just 1 inch falling at Burlington, for example. You can see how that's been hooking up, and that is definitely related to a couple things: higher water vapor, and the fact that we're getting weather patterns that are featuring heavier rainfall because of the jet stream configuration, and that's related to the loss of Arctic sea ice. Occurrence of high flow in the Mad River Valley, on the Mad River itself. 10 more days per year, and that is projected by 2100. The crazy thing I've been hearing in climate is that the new 2100 is actually like 2050. So the Earth's starting to catch up on its temperature. And this is, of course, measured the global land-ocean temperature combination anomalies. The red is warm, the blue obviously cool, and you can see where we got. And I want to call your attention, it's very interesting. You see the little, sort of about 1940, you can see that little bit of a sort of uptick there, and then a downtick, and it kind of back and forth, natural variation, kind of the typical kind of thing. And then we really started to shoot up right about 1975, 76, 77, 78, 80, right? Guess what happened then? We had the Clean Air Act that was passed, a great thing. It lowered the amount of smog, but it also took soot out of the air, and when you take the soot out of the air and you allow free sunlight to then interact with climate, with the global greenhouse gases, well, it excites those molecules and generates heat. Off to the races. So oddly, yeah, if we had a more polluted atmosphere, that's what was masking that. From 1950, you can see how the temperature warmed, and then kind of industrial pollution. You can see how it basically kind of took, what, 40 years? So that period was because we had particulate in the atmosphere that was reflecting back to sunlight. Take that particulate out, and what you end up having then is free sunlight and a rising temperature due to carbon dioxide. So the temperature is starting to catch up, although not evenly around the globe, and it's in fits and starts. And you notice here the annual temperature anomalies are much warmer up at the top of the globe there in the Arctic. So what happens in the Arctic doesn't stay in the Arctic. These are Arctic temperatures for the records. You notice that you start out with, 2 is February and so forth. You see it all the way to December. So in the middle of the June through August, you see kind of a dip there. So the Arctic temperature record high, basically from 70 to 90 north latitude, way up there from 1950 to 1980 baseline, the comparison is that the temperatures have been going up in the Arctic during when? The winter. This is today's shot that was just taken from the climate reanalyzer. And I just want to call your attention. You can see that in the Arctic, how warm it is above normal. Right now we're into, that looks like a little bit of a negative AO or Arctic oscillation. But what it does is it displaces a lot of colder air south. And you can see there's some blue there. Incidentally, that blue was 45 to 50 below zero around Alberta and British Columbia. And I was looking at it today. I'm going to be headed out there actually on Saturday. I was kind of hoping I'd hit the worst of the Arctic air, but unfortunately we're going to miss a little bit. But that is some really cold air, and that's what's going to be here at the end of the week, my friends. Oh, so why is it being, what's the deal? Why is the Arctic warm, compared to average, right? Versus the cold. And look at how warm it is in the eastern part of North America. So why is that? Well, the jet stream is gone bonkers. It's slowed down. And that jet stream slowing down creates very large oscillations. And when you have that large oscillation, it takes the Arctic air that should be over the Arctic, displaces it to 45 north latitude where we live. So this is kind of the average temperature anomaly, December, January, and February over the past 25 years. You can see that those averages show that they're above normal from the baseline. And notice where the colder air has settled into Siberia and parts of Asia, Eurasia. And then take a look at east of the Rockies into the United States, Great Lakes, and we're kind of on the edge of that. That has been the climatological trend lately. Should be warming, right? What's up with that? It should be warming. Now, remember, this is winter time. So during that time, we're actually seeing a signal, and this is very young science, because we haven't lost the Arctic sea ice since 1980, so we don't have a great data sets. And there's a lot of controversy about this. But in fact, what ends up happening is that the warming of the Arctic is displacing that colder air as the jet stream is pushed further south, and hence, that's why we're having more extreme weather. So this is the Arctic again. You can see the ice cap. This was, so far, the 2012 was the minimum sea ice extent. And when you have open water like that, at that point in time, it takes a long time, that ocean water to warm up, melt that ice, have the weather systems correct to pull in warmer air from southern climes and whatnot into the Arctic, starts to melt that ice, and that's what happened in 2012. We had the best of all conditions. We're very, very close to that right now. So what ends up happening is sol will hit the ice. It reflects the albedo, okay? I'm sure we've all seen this before. You want to melt snow a little faster, take some black particulate, throw it in the snow, it'll melt, right? So what ends up happening is, in a perfect situation in the Arctic, with a perfectly white and very strong albedo, that reflectivity would then reflect back out to outer space. That's not happening now because the ice is melting. So what you end up having is the sunlight goes in, the energy goes into that dark, dark water, and it heats it up quickly. How unusual is this? And that's 2012, and you can kind of get the picture, but that's kind of a short range picture. Let's look at maybe in a longer range picture. You see what I'm saying? Okay, so here's where we are right now, 2020. So if you take the light blue line, which is 2019, it's on the bottom there. This is January through December, the season. And you can see that the maximum ice in the Arctic is during when? February, late February, March. When do you think Mount Mansfield has its maximum snow? The snowpack builds up when? About the same time, right? Maybe a little bit later, elevation dependent. So then you go, when's our warmest time of the year? Well, typically for us, it's, June, July, August. A little bit offset there. It takes a little harder, a little more energy to heat the water, the Arctic Ocean. And so you see the dip, and then basically as we get colder, there should be more ice being made, right? So more ice is being made, but you can see that also the ice is at some of its lowest levels. The sort of fuzzy line there, the sort of solid opaque line, the gray line is where we should be, and those are 2 standard deviations. And we're around 3, 4, maybe about 4 standard deviations. That's pretty significant. So near surface air temperature in the fall, you can see that in the mid-latitudes. It's a little warmer lately. It's warmed up after 1980, again, that soot thing I was talking about. But you can also see that in the Arctic, it really jumped up. We draw the line. So when we consider a layer of the atmosphere stretching from here, that is, say, the warmth of the Bahamas, where it says warm there or something, and then how the atmosphere is much thicker where it's warm. The atmosphere, when thunderstorms form, for example, you have the atmosphere thickness is extreme. So you have tops of the thunderstorms that are sometimes 50, 60,000 feet. That's nothing unusual in the tropics. However, back north, where it's much colder, the atmosphere is much thinner. So it doesn't take as much, it's just the thinness of the atmosphere is part of what is some of the physics around this. So what we have is an Arctic that's warming, right? Compared to down in the middle latitudes. So that yellow line kind of represents now. You can say maybe the blue line represents the older days. And consequently, high latitudes are warming faster. And it's slowing down the jet stream. And it's been measured in basically in metrics showing this now. That OND, that's October, November, December. So that's the peak effect of the loss of Arctic sea ice and what it's doing to the jet stream, the zonal wind. And it does mimic, it's not 100% correlated, but it's pretty close. This is some of the work produced by Dr. Jennifer Francis and Steve Vavris, and she's from Rutgers and he's from, I think, University of Minnesota. And the paper came out in 2012 and enlightened everybody. And there's been a lot of body of knowledge since then, but it's very controversial. And the reason it's controversial by other climate scientists is because simply there's not enough data set. We haven't had enough time to go, yeah, that looks right, because they like big time data sets. Well, the Arctic sea ice has only just melted since about 1980 it started, and now we're off to the races. So the Rossby theory here is the weaker westerly flow favors more meandering pattern, slower eastward wave propagation. So instead of having a jet stream that kind of circles the northern hemisphere, maybe a little short waves kind of go, you get these big giant undulations, all right? It's kind of like the rivers when they hit a flat spot. They have a tendency to meander. It's the same kind of fluid dynamics, air or water. So the effects of AA is not Alcoholic Anonymous, but Arctic amplification. Arctic amplification is what's going on in the Arctic. It's warming at 2 to 3 times faster than the rest of the planet. And we saw that with some of those temperature scenarios. So it causes basically weaker westerly winds, a slower jet stream, and it intensifies the troughs too, but mostly the ridges of higher pressure have a tendency to expand. And so California, you think California with its West Coast droughts and whatnot. Right now, of course, everybody's fresh in their mind as you think Australia, same kind of thing. Antarctica is doing the same thing now in the southern hemisphere as it's doing it in the northern hemisphere. It's been delayed a little bit. It was a little later start because Antarctica is a continent of land with a lot of 2-mile thick ice. And of course, the Arctic Ocean is just an ice cap, and it's very thin in terms comparatively. So as the high latitudes warm, middle latitudes you get this sort of thing. And that's what we're seeing now. You see how those ridges are expanded further to the north? And that basically makes this. And this is why our weather's all screwy. So an example from Jennifer Francis, basically showing a ridge along the west coast. Let's think of it's called a Pacific North American PNA plus. When it's negative, there's a lot of storms coming into California. So in this particular case, the jet stream would ride north, and all the moisture from really the Pacific would ridge up into Alaska. And then California and the west coast would be under drought conditions if that stayed there permanently. Nature's carbon tax. So that's kind of what we're getting right now. There's a budget of energy, there's a budget of carbon, and we're sort of undergoing that right now. But you can see that 2019 is not the worst, but 2008 was from 1980 to 2019, the year to date, that's the billion-dollar disasters. You can see that we're not at the worst, but still pretty bad at this point. And of course, it does things like this and affects us here in Vermont. Selective climate anomalies. Now, some of these I'm gonna go through really quickly, but this is just for the month of January. They have the month of February, but they stopped. I hate to say it, but I think it's political. It means the data, they're just kind of putting a clamp down on it. Maybe I'm wrong, but I'm suspicious. They should have had the, March, April, May, June, July by now, but they don't have it. So one of the things I want to call attention to right here, you can see all these little red kind of ball things. That's temperature records. Take a look at that across the world. A lot of places seeing that. Antarctic sea ice extent, you can see, or Arctic sea ice extent up there in Greenland, Iceland area there, and so forth. So keeping that in mind, of course, this is January 2019. The top climate hazards, as we head into 2050, 30 years from now, you can see that basically what we're looking at, our problems are precipitation. Our problems are probably a little bit more included in that would be severe weather and erratic winters and maybe very large blizzards, very large snowstorms that we haven't seen yet. The kind of snowstorms that might have infrastructure problems where barns collapse and this kind of thing. Think of the St. Valentine's Day storm, how much snow fell. We're seeing more of this across the planet. Why? Because there's more water vapor, check that box. There's also screw jet streams, and sometimes these jet streams cause much slower moving storms, and if that storm is unloading over you for a longer period of time, it's gonna be more extreme, it's gonna break more records, it's gonna unload more water or snow. So we're gonna go month by month here and just kind of visit along here. So if you remember back, this is overall 2019, so I haven't gotten that point yet, but California, the big deal. Notice the concentration more or less in the kind of the middle part of the country, east of the Rockies for the most part, but not so much in the Northeast United States. We haven't really seen a lot of really bad climate disasters here. It's been just a little to the west or a little to the south, major flooding. You figure Iowa, the things that happened in the spring, for example, or think about the California wildfires compared to what we had here in Vermont. We complain about 65-degree temperatures and a loss of snowpack. Of course, it ruins the economy, it makes us upset, but it doesn't burn your house down. Okay, this is the month of January, and we're going to kind of roll through these kind of quickly. You're going to see a lot of these here. We got 11 of them, I believe. You might keep an eye on Alaska. Bering sea ice extent, second lowest on record. Record warm temperatures along the west coast. Because of that, that's a feedback. And then you're looking at craziness, okay? You're talking about record warmth and loss of sea ice. And then you go down to Arizona, snowiest single day on record in Flagstaff, Arizona. Displacement, screwball jet streams, bizarre extra moisture, more to go into snowfall just because the temperature is below freezing. Warmest March on record for Alaska. Earliest 70-degree temperature in Alaska of record. Meanwhile, major winter storm in early March, over 1 foot of snow across Connecticut, Rhode Island, and Massachusetts. You see a pattern here? Kotzebue had the warmest April on record. Tanana and Kuskokwim rivers had their earliest ice breakout on record. And then you're looking at Seattle, April record, 12 consecutive days of rainfall. Why? The jet stream got pushed south, picked up that Pacific moisture and pushed it in, right? So you're seeing this kind of, things are happening up in the Arctic and the northern regions. And then there's a response down further in the lower 48 United States and down in our neck of the woods here. So we're into May, and look at that, Alaska again. 6th warmest May for Alaska. Part of Southwest Alaska, an extreme drought for the first time in more than 20 years. Meanwhile, we're looking at record-setting heat wave in the southeast United States, earliest 100-degree day on record for many locations, et cetera, et cetera. In June, there's one for you. This is a little anomalous, I guess. And that is, you can see that in the Montana, Idaho there. More than 1 foot of snow fell across parts of the northern and central Rockies on June 20th through the 22nd. Wow. But it's high elevation. Things can happen in high elevation still. And then severe weather, flash flooding, June 20th, parts of Pennsylvania, New Jersey, Ohio, and Illinois, and so forth. Also keep your eyes on Hawaii too. They've been having very ups and downs in terms of stuff going on over there. So for example, Hawaii, sea surface temperature departure from average above Hawaiian, across the Hawaiian region remains well above average for July. That's why some of those hurricanes that form off Mexico are now making it pretty much on a regular basis, either a little bit to the south of Hawaii or sometimes to the north and sometimes right over it. So that's another issue. That's a climate change relationship because of warmer sea surface temperatures. You got Tropical Storm Erin off the east coast there in North Carolina and so forth. And then still looking at Alaska, 2nd warmest summer on record for Alaska, amplifying the drought, blah, blah, blah. See the northeastern interior sections. And of course, it contributes to what? Wildfires. So we're into September now. As I recall, September around here was about one of the more fabulous Septembers. Everybody remember that? We had great weather in September generally. So Northeast, no problem. But look at the other places. Significant winter storm that brought up to 4 feet of snow and blizzard conditions to part of Idaho, Montana, and Wyoming during September 28th through the 30th. Anybody have an idea as to why? I'll tell you why. Because there was Arctic air that was displaced southward. And again, it caused near 45 north latitude, we had more storms going on. Okay, we're in October and kind of just more of the same. Keeping your eyes on Alaska, and then also, let's see, Hawaii had Kahului, Honolulu, Lihue had their warmest January through October on record. That's interesting because it takes a lot of energy to heat up the Pacific Ocean way out there off in the middle of the ocean, basically. So that's a significant deal to get that kind of energy to heat that, to produce that kind of a record. Okay, we're getting close to the end here. Let's see, we have, this is November. Remnants of Tropical Storm Raymond. We got Puerto Rico remained drought-free during November. A small area of moderate drought emerged in early December. They had been getting really bad drought there. Of course, that followed the tremendous Hurricane Maria a couple years prior. Poor Puerto Rico, they've been just, and then they get seismic activity, and earthquakes, and they're just getting all ways. But notice a strong low pressure system, a nor'easter off the East Coast brought coastal flooding, beach erosion, North Carolina Outer Banks to New England, ice, snow to the Northeast. That was November 17th through 19th. And yes, our November was like our winter. And ever since then, it turned. So this is mean temperature percentiles. And what we're looking at here is January through December, the entire year of 2019 and so forth. Looking at precip, that's what it looked like. So it was a wetter year for us. So some of these correlations are related to how warm the Arctic gets. So they went back and they did a study, and this is just one part of this study, but what it shows is every time the atmospheric cap, the polar cap we call it, the heights, it takes warmth to create those heights to rise, just as we were showing you that jet stream squirrely thing with the two lines and how it's been rising because it's warming much faster in the Arctic. Well, that warming has also been correlated with each one of these extreme weather events. Pretty amazing stuff. So there is some kind of correlation going on there. That's why what goes on up in the Arctic doesn't stay in the Arctic. So here's some of the emerging mechanisms. That's, why is it getting cold in November? What is up with that? Well, Dr. Judah Cohen of MIT, Atmospheric Environmental Research, I believe it is, AER, has been working over the last, I would say, decade and a half on trying, his whole thing is to try to predict the winter, long-range prediction. And what he has discovered is that there are mechanisms that are related off of Siberia in the Arctic Ocean there, that when snow it's called the SAI, when Siberian, I forgot what that means. It's an index. And what it means is basically when there's a lot of snow in Siberia during the month of October, if it happens fast, his winter prediction is that we're going to have a tough winter here in North America and some parts of Eurasia, etc. If that snow laid down during the month of October only is slow, we're going to have a warmer than normal winter. Well, this year it came out really on the edge, 50-50. We kind of had that sort of thing going on in November. Now it's kind of toasty, but we might be going back into a colder cycle now. So this emerging mechanism basically goes like this. AA is the Arctic amplification, meaning a warm Arctic, okay? So you get earlier snowfall along the coast. This promotes a trough of lower pressure. That wave energy transfers to the stratosphere above the troposphere. So where our weather is basically located, where airplanes fly, even the high jet stream, that's all in the troposphere. You get above the tropopause, it's roughly, depending, goes up and down, just like we talked about atmospheric thickness. Well, typically it's above the jet stream levels where the stratosphere is, okay? So that's the top or the ceiling of all the weather. So up in the stratosphere, we also have a thing called the polar vortex over the pole. And when energy is reflected from the ground through the troposphere into the stratosphere, it does this. Basically, the polar vortex is weakened. That's in the stratosphere. And then it weakens the polar vortex down below in the troposphere. It's like a boomerang effect. It takes about 2 weeks to a month. And you get a wavier jet stream. That wavier jet stream promotes a weaker polar vortex at the surface in the Arctic. That releases all that cold air. And guess where that cold air goes? Through Alberta, east of the Rockies, the Canadian Rockies, and so forth, and right into sometimes the upper Great Lakes, sometimes right into our neck of the woods. And typically when they get cold in the Great Lakes, we'll probably get cold too. And so that's the mechanism that he discovered with his long-range forecasting. Judah Cohen. He's brilliant. Okay, and that mechanism affected us last March. This is Lake Champlain, completely landlocked. Remember I showed you all those diamonds about open ice? We got a new curveball going on. That new curveball means our winters may be actually getting colder. Shocking. What's this global warming thing? No, it's because of the global warming. So if you connect the dots, it basically is this, all that energy going to the ocean is melting ice. That causes energy that reflects up the stratosphere. That energy in the stratosphere weakens the stratospheric polar vortex, which then boomerangs down, takes about 2 weeks to a month, weakens the polar vortex, releases all the cold air, which is now coming through Canada right now. I showed you Alberta. That's an example of it. And it's headed our way, and it will be here late in the week. That is exactly what's been going on. And that's what happened in March 1st, which there was no ice, all the ice rather. It was completely no open water on Lake Champlain. So Arctic amplification is alive and well. High latitudes are warming much faster than the mid latitudes, especially in fall and winter. Poleward thickness gradient is weakening. You get zonal mean flow at 500 millibars, which is about the cut halfway in the troposphere, if you will, at 18,000, 20,000 feet, which is a kind of halfway point is what they use as a measurement, 500 hectopascals or millibars. It weakens, the flow meanders more. Peaks of ridges are elongated northward. The work from Jennifer Francis is done, Steve Vavris. You're getting these up and down motions now, this sort of configuration of the jet stream that's kind of crazy. More amplified Rossby waves should progress eastward more slowly, increase the likelihood of blocking. When you get blocking, storms come to a halt. Uh-oh, what happens when a storm sits over you for days? Think Hurricane Harvey. See the connection? Weather conditions are more persistent. Let's say it's a ridge of higher pressure. That ridge of higher pressure is going to produce what? Drought. So, unfortunately, greenhouse gases warming the atmosphere, messing with the configuration of the jet stream, is causing simultaneous droughts and simultaneous flooding, or simultaneous big snowstorms. Increased probability of extremes, cold spells, heat waves, flooding, prolonged snowfall, and drought. Greenland Ice Melt 2019, this was this summer. You can see that the 1981 to 2010 medium was the dashed lines there, and then the 2019 melt percentage. You can see how just extraordinarily lots of melt, lots of water runoff, right? That's what it looked like on the edges there. It was kind of melted back. And then, again, this is January 1st through August 13th. And this is quite amazing because the greenhouse is it's a big continent, really. I think I'd consider it an island, but it's a, you know, it is a, the number of melt days have gone up a lot. So much so that they actually have little tiny forests on the edges now of Greenland. And I think they've been there before. It's part of the oscillation of natural variation, but those forests, because of our screwball jet stream and blocking areas of higher pressure, have caused forest fires in Greenland. And lots of runoff. Okay, back to a little bit more closer to home here. So, it's weird. It's crazy to say this, but because of climate change, we might be seeing bigger snowstorms. And actually, those years that we have the setup right, fabulous snowfall. Colder winter, fabulous snowfall, but our winters are not consistent. There's no persistence to them. There's these ups and downs. Again, that jet stream moves along eventually. The cutoff low gets kicked out. The next one tries to set up or whatever. And so there's a lot of variability. And so the name of the game with our winters is going to be variability. It's going to be 1 year is going to be totally different than the next, or say 2 in a row, this kind of thing. And this is the trend of what's going on. Again, what is it related to? The loss of sea ice. This is a little bit bad. Okay, this is going back to the El Nino year, 2015, 2016. And this is the top of Mount Mansfield. of the average snowfall at the stake. This is the snow depth, I should say, not snowfall. So what you're getting here is you're seeing it was pretty low, that you can see how bad the season started out. Everybody remember that 2015, how the winter started out? The winter 2015 was just disgusting. It was a very poor year for skiing and all that. This, on the other hand, was another year, 2018 through 2019. That was last winter. Look at the amount of snow at the stake. Completely opposite. Variability. See that? Here's where we are as of today. The hump, the green hump there on the left, there, the mountain on the left, that's of course average snowfall. And then you can see where we are as of just a couple days ago, the 12th. And we're not starting out too well. And the reason for it is because of systems that look like this. You get these big oscillations. The big ridge of higher pressure pushes north. Downstream, it produces a big trough of lower pressure. Sometimes it cuts off from the jet stream. And then you get that business. And this particular stuff typically ejects energy over the flat ridge. And that's also how we get ice storms. It's not a good setup for us. So in general, this is, you might notice, this is the extreme weather events across the world caused more than $100 billion worth of damage in 2019, but we can't do a carbon tax. I find that really funny. Notice it's the fires, 25 billion, California, October through November. 12.5 billion in the Midwest there. That was, what was that? That'd be floods. That was in spring, March through June. And then you got other various types of weather. And then in Asia, you're seeing the same thing. It's costing a lot. It ruins infrastructure. Magically, people think that, oh, there's global warming, we can't do anything about it. It's too costly. You can't do anything, it costs too much. Well, that's what's going on right now. What is the logic train, I would ask? What is the leaders? What are the politicians? What sort of logic train are they using? That's Mozambique, tropical cyclone Ida. A lot of heat going on in Australia. I'll get into a little bit of that here a little bit later on, but we're getting closer. So this is like paleoclimatology, past and current abrupt climate change. So the Permian-Triassic Extinction 250 million years ago was geologically instantaneous. And what they mean by that is that it happened very fast. It doesn't do this nice sort of curve and linear kind of thing, you know. It's like it goes along and all of a sudden it jumps. It goes on again. That's called abrupt climate change. Lots of evidence in the paleoclimatology record that we're in for some big jumps. I'm going to go back to that because there was actually a little bit more. Okay, so the Paleo-Eocene thermal maximum, initial temperature, that is the Siberian traps, where the volcanic activity, for whatever reason, a continental seismic activity, lots of volcanoes went off. And when the volcanoes went off, they put up a lot of CO2 and they raised the temperature. Okay, they raised the temperature 5 degrees Celsius, 56 million years ago. They may have been over less than 2 decades in terms of the abrupt climate change that took place then. It caused, I think, the 5th mass extinction. And then the additional rise of 2 to 5 degrees Celsius is projected over the next 80 years. That's according to the IPCC, back the latest data that came out in 2014. However, a much faster scenario is likely given trends and difficulties to account feedback mechanisms, which I'm showing you one of the Arctic ice and how it's screwing with the jet stream, creating colder winters, but on a variable scale. So, a globally accelerated climate change global warming event. We're waiting for one. Might be happening right now, might actually be happening with this last go around with all the fires in Australia. So just to recap, we got sea ice extent down. That's the Arctic. We got Greenland ice mass loss. We got Antarctica also mimicking the Arctic now at pretty fast rates with mass loss as well. We got alpine glacier ice mass loss. We got sea level rise going up. We got hurricanes that are slowing down and sitting over one particular island and just absolutely taking everything, almost leaving the soil. That's Grand Bahama. That was Dorian. Everybody remembers Dorian. And I don't want to get into this too much, but tropical cyclone behavior threat, this is if the world rises on average to 2 degrees Celsius. Remember, we're not there. In fact, the world right now, using climate reanalyzer, I saw was about 0.8 of a degree above the 1980 to 2010 baseline. So they figured these are the things that would happen, but they're already starting to happen at 0.8 of a degree Celsius. This is predicted to be at 2C. So this is Mozambique, Cyclone Ida. And a reminder, abrupt climate change is one symptom of ecological overshoot. Abrupt climate change is, these are the symptoms here: topsoil loss, natural resource depletion, ocean acidification, mass extinction, global toxicity, I should say, chemical nuclear plastic pollution, growing social economic inequalities, economic instability, political instability, rise of authoritarianism, not just around here, it's all over. Symptom cross feedbacks, and each one of these symptoms amplifies each other. Australia, look at their temperature rise, would you? Australia Fire Danger Index. These are the changes in fire weather index, or weather risk, I should say. And you can see that there's certain spots that are not doing too bad in the center there. I don't think anything grows there. I think that's where the desert is. There's nothing to burn. And then on the other side of the scale, you have flooding. That was this spring in, I think it was Oklahoma. Climate solutions. There's actually a little bit of hope. It's amazing. You know, on a personal level, I'm very depressed. Any climate scientist, anybody dealing in the work that I do in meteorology on a day-to-day basis and in climate basis is very, very sour. People aren't, you're Cassandra. Nobody listens, nobody wants to do anything. Everything just continues to bumble right along as if you're just talking to the wind, you know. But there's actually some solutions now. The first solution, and there's not a lot of data, this is all fairly young and fairly new, is iron filings in the ocean create mass plumes of phytoplankton. Those mass plumes of phytoplankton pull out more carbon dioxide out of the atmosphere than anything imaginable, turns out. If they could mass produce some of this under the certain, there are limitations, ecological limitations, the water temperatures have to be such and such and this and that, but under those situations, this is something that needs to be explored pronto. We don't have any leadership. We have to go around the leadership, our so-called leadership, which is not leading. So we need to circumnavigate. You know, people, businesses, people want to make money. There'll be money to be made in this sort of thing too, lots of money. This is the other new thing that we found recently, is that lo and behold, in Iceland, they started to capture carbon dioxide out of the atmosphere and pump it deep in Iceland, in the volcanic chambers there. And lo and behold, they discovered it makes limestone. Well, guess what? There's companies that now can use that limestone to make cement. They don't have to mine limestone anymore. If we had this on a mass scale, pulling CO2 out of the atmosphere, we could change things through these sort of technologies based on the mass scale. This is that one of those companies is called Blue Planet. And you can see the rings around this kind of thing. That's actually carbon dioxide being pulled out of the area around San Francisco. So what this company has done is they've worked with this carbon dioxide sequestered aggregate, they call it. And the last picture here on the right-hand side is a taxiway that they built with that carbon dioxide pulled out of the air by this company on this taxiway in the San Francisco International Airport. Pretty awesome, yeah? Why can't we repeat this on a mass scale? Where is the leadership? Where? And that's what we have. And so what we got to do is we have to take that 500 parts per million right there. That's the problem. We got to push that down to 280. If we push that down to 280 with new technologies, I hate to say this, and you're going to think it's blasphemy. You could pollute until you could have all the carbon dioxide, the oil, the coal, you could burn straight coal. As long as we pull it out of the atmosphere and keep it at 280 parts per million, we're good to go. Except that coal is very nasty and there's other side effects and we don't want to do that, obviously. We want green, renewable energy. But you would think that the fossil fuel industry would get behind some of this so they can continue their business model. You would think. And that's it. Thank you very much.